Hi everyone, this lesson is about adjacency matrices. Now a matrix is just a grid of numbers, and we use these matrices as an alternative way to represent the information shown in a network or a graph, such as the one we have here. Now before we get into this, what we want to do is list the vertices. So we have L, M, N, O, P, and use the same order for the rows. L, M, N, O, P. And every entry in this matrix is going to represent the number of connections or edges between vertices. So let's take a look here with L. So L does not connect to itself, so L is a 0. L connects via one edge to M, so I'll put a 1 there. L connects via one edge to O, and L connects via a single edge to N. There is no direct connection from L to P. There is no single edge, so that's a 0. And that's our first row. Now we can just keep going row by row by row. Vertex M connects to L. Now, we've already looked at that edge. That number there corresponds to the same edge there. In fact, those two number ones both represent this edge in the graph from L to M. So there's going to be a duplication when we do the entire matrix like this, but that's just part of what we do. Where do we get to? M connects by a single edge to N. M connects via two edges to O. That's multiple edges there. And there is no direct connection to P. Once again, there's a 0 there because M does not have an edge that starts and finishes at M without passing through other vertices. Let's go to N. N connects to L. N connects to M. N connects to P. There's only 3 edges, or the degree of vertex N is 3. That should be it. N does not connect to itself, and N does not connect to O. O connects to L, one edge. O connects to M via 2 edges. O connects directly to P via a single edge. Now there's 1, 2, 3. The degree of vertex O is 4. If we add them, we get 4. The other two should be zeros. O does not connect to N, and O does not connect to itself. Vertex P does not connect to L. It does not connect to M. It does connect by a single edge to N. It does connect by a single edge to O. And it does connect to itself. There is a single edge that begins and ends on vertex P. So vertex P has a loop. This entry way down there, actually I might highlight all of the entries here as this colour because they are the lead diagonal. So the lead diagonal is a vertex connecting to itself. That's why we have to have the vertices listed in the same order for the column headings and the row headings. Now, usually vertices do not connect with themselves. Usually they are zeros. In the case here where we have a loop where a single edge starts and finishes at the same vertex, that's where we're going to get an entry on a lead diagonal. So loops are easy to spot in the adjacency matrix. They appear on the diagonal. Now let's go through here. Remember we said that the entries in the lower triangular part have a corresponding entry in the upper triangular part. That one would correspond to this. That one there would correspond to this. The 0 there would correspond to this one. It's like a mirror. The diagonal is like a mirror. and we should find that it is symmetrical. Every entry in the lower triangle has a corresponding entry in the upper triangle. There they are. So imagining the diagonal there as a mirror, and each entries reflect. Now that leads to probably a bit of a strategy. If I were to be doing an exam and I wanted to draw this adjacency matrix, I went row by row by row, but I actually did twice as much work as I needed to. I could have started with the lead diagonal. There's no loop there, no loop there, no loop there, no loop there. Yes, there's a loop, so I would have had 0, 0, 0, 0, 1. Then I could have focused just on the entries here in the upper triangular part of the matrix. Once I had those under control, I just used my little reflection to fill in the rest of the matrix quickly. That would be a faster way to have solved the problem. Let's try the opposite problem now. Let's try drawing a network from the given adjacency matrix. So I can see there are 4 vertices. Oh, what happened? So I'll begin W, X, Y, Z. And I'll begin looking down the lead diagonal. 0, 0, 0, 0. There are no loops involved. Now I'm just going to concern myself then with the upper triangular part of the matrix, because as we've just said, if I get those connections, that's the network. I can see that it's symmetrical. Now let's have a look. W and X, there's a 2. This means there are 2 edges connecting W and X. W and Y is a single edge. W and Z, there are no edges. Let's move to the next one. X and Y is a 0. There is no connection between X and Y. X and Z, there is 1 edge. Lastly, Y and Z, there is 1 edge. That's my network. Now, if I was to look at the ones at the bottom, I would find exactly that information is already drawn. I do not need to draw it twice. In fact, it would be a mistake to put more edges in there. That's a quick introduction to networks and adjacency matrices. You should be familiar with going from a network to a matrix, or a matrix to a network. And look out for things like lead diagonals, upper triangles, lower triangles. Zeros along the lead diagonal mean no loops. If there is a 1 anywhere on the lead diagonal, like we had there, it means there is a loop at that vertex. Okay, that's it for now. Thanks for watching.